Yes, hello dear students. Today we are going to discuss about the surface tension. In that first, what we are going to discuss means we are going to discuss about the cohesive force. Cohesive force. What is meant by cohesive force means the force of attraction between molecules of same kind. The force of attraction between molecules of same kind is known as cohesive force. Next, what is meant by adhesive force, which we have to know here? What is meant by adhesive force? Adhesive force. So, what is meant by adhesive force means the force of attraction between molecules of different kind is known as adhesive force. Adhesive force you can tell. For example, let me take one example to make you understand. Let me consider a container here. One container we are having. This container, what is that means here? Let us take up to here water is filled here. Water molecules. This is what? Container. Now, for example, if I consider here what will be there means water molecules. This side, this around that what will be there means water molecules only will be there. So, in the type of molecule, which type of force will be there? For example, in this side, cohesive force is there means in this side also cohesive force, because surrounded by that what particles is there? Water particles only, right? Fc, water molecule, because water molecule Fc, cohesive force, cohesive force, cohesive force. In all directions, what will be acting is here? Cohesive force only acting. See, if you observe here now carefully, so this force, 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 all the forces will get cancelled. Therefore, sigma Fc equal to how much means 0, we can tell that. Or F net equal to how much you can tell that? F net also equal to 0, which you can tell here. Now, if you observe here now, for example, we need to check force about this point here. If you want to check about the force here now, so this is water molecule, downside completely water only is there here. So what will happen means in this direction Fc will come, in this direction Fc will come, in this direction Fc will come. But if you observe here now, in this direction Fa will come, in this direction Fa will come, in this direction Fa will come. Why Fa will come? Why adhesive force should come means this is water molecule. Here all the particles are air molecules now. That's why. In generally, what will happen means Fc should be greater than Fa. Fc should be greater than Fa means what will happen? Fc is acting downward. Fa is acting upward. Fa is acting. Na? So what will happen? F downward is greater than F upward. So as a result, what will happen? Here downward forces acting downward more. Upward forces is less. For example, if I take here, no, here also like this it will come. Fc, Fc, Fc. Here what will come? Fa, Fa, Fa. As a result, all the downward forces will be more, upward forces will be less. So what we are able to observe here means we are able to observe like this. For example, this is that water container. So this will be water molecules, layers. That upper layer looks like deep pressure, like this will get it, Nana. Due to what means due to this cohesive force, adhesive force only, that upper layer looks to be disappear. Fine. Let me conclude that point here. Upper layer of liquid liquid appears to be depressed. This phenomena is known as surface tension. This phenomena is known as what we call surface tension. So then, how can we define this? Means definition. So we can define like this. The force acting per unit length is called what? Surface tension. The force acting per unit length. So surface tension symbol I'm giving T. Some people can give S also. You need not to worry about that. So any symbol you can take. T equal to what we can write here? F by L we can write here. Force acting per unit length. T stands for surface tension. Now we need to discuss about the wetted perimeter. We need to discuss here. Wetted perimeter. Wetted perimeter. So what is meant by wetted perimeter means where solid, liquid, gases are in contact. Now that perimeter is called what we can tell wetted perimeter. Perimeter where all three states of matter, solid, liquid, and gas are in contact with each other. For example, let me take one container here. In this container, up to here we filled with the water. Now what we are placing means we are placing here one ice cube, let us take. One ice cube is floating like this, let us assume. If you observe here, now in this perimeter here, this surface, and backside surface, and this corner, front, right side, back side, and left side. These all the faces are in contact with water, and the ice cube itself solid. Outside it is called air. This surface is called what we can call it as wetted surface. So we know that what we know that here T equal to what we know here F by L we know. So F equal to what we can write T into L we can write it. If I take cube length is nothing but let us take like L here. So what will happen here? Length L, backside L, backside L, side L. So how many sides is contact with the water? 4 sides. That's why your wetted perimeter is how much you can take? 4L. Therefore, F equal to what we can write here means T into 4L, which we can write here. T into 4L, which you can write here. So here, F is nothing but what? Force due to surface tension. Force due to surface tension, which we can tell here. So and T is nothing but what here? Surface tension. L is nothing but wetted perimeter, which we can tell here. For example, what we are having here, F equal to what we are having, F equal to T into L. So this is standard formula which you have to remember here. F is nothing but just now you got to know. What is T indicates means T will use it about the direction tangent parallel to the surface. So what does it mean? direction tangent it will give sana. And what is the direction of that means? It is parallel to the surface. For example, let me take one stick. One example. Let me discuss here. What does that example gives means here? In that example, what we're going to discuss means we're going to discuss about one matchstick. Matchstick or needle. So what is going to be matchstick or needle example I'm telling means here? We having one container we having here. Up to here, what is we fill means? We fill some liquid like this. Here what we are placing means here we are placing one matchstick nana. That's why it is depressed. If you observe this nib now, here you can able to observe the tangents. Let me show you the tangents outside clearly. You can able to, I'm zooming the tangent point and observe, you are going to observe this. You're going to observe like this. About that head, matchstick head. If you observe here, now in this direction what will come? Tangent will come. TL. In this direction what will come? Tangent TL will come. So this is we consider like needle or this matchstick we are considering like what means here? Point object which we are considering here. Point object. Object or thin object. So if you draw free body diagram for that clearly, so whatever you are able to get means you are able to get like this. This is matchstick. For matchstick downward, what will be acting here? For downward, what will be acting? So Mg will be acting here. Upward, what will acting, Nana? About this point, tangent TL is acting force. About this point, tangent TL will be acting here. So what we can write it here? TL plus TL will be what we can write it? 2TL. Therefore, 2TL equal to Mg we are having here. So this case, what we get law here? 2TL equal to Mg. F equal to 2TL, you got it. That is balanced by what? Mg. So for example, if we want to take that object out of the water, what required means we need to apply some extra energy. That energy is we need to supply energy. For example, let me take here. If we take point object, that is needle or matchstick from out of water. For example, we are having case. This is a case. Container will be having. So what is happening means from this, what we are going to take means that matchstick is there, right? I want to take outside that matchstick. I want to take outside. If you want to take outside now here, what you're able to observe means the tangents will get like this. And observe carefully. TL, TL. So if you want to pull it upward direction means since tangents and the force also acting downward, now what will happen means the object will try to stick to the liquid. The object will try to stick to the liquid. So when the object is tries to stick to the liquid, what we need to apply? We need to apply the extra energy, right? That extra energy is called surface energy, which we can call it as extra energy required to pull it back is called what we can call it as surface energy. Let me conclude about this here. Therefore, the extra energy or work done required to remove object from surface is known as surface energy. Surface energy in brackets symbol is W. Therefore, work done equal to what you can write general formula of force into displacement. So force is due to what? Force due to here surface tension you have to write. Force due to surface tension. Therefore, F equal to what we can write? Work done equal to FL is nothing but TL, right? TL into ds displacement. So this L into ds can be written as what? Area. Therefore, work done equal to T into dA. So this is the surface energy formula in terms of surface tension. Our work done can be written as T into change in area. We can conclude dA means change in area of the surface, which we can remember. And this formula is very helpful while deriving the equations. So first what we have studied surface tension. In that cohesive force, adhesive force. Cohesive force means force between same kind of molecules. Adhesive force means force between different kind of molecules. So if you observe in this case, F upward is less than F downward. No? So F downward is more means that upper layer looks to be depressed. Definition means force acting per unit length is called surface tension. I'm giving symbol T. Wetted perimeter means where solids, liquids and gases are in contact. So about this point, these all contact. Now let me take one example, another example here. Matchstick or nail if you want to keep on the surface of the liquid. No, so these are the tangents you're getting. If I draw P-bar diagram, you'll get like this. Upward force, how much you're getting? 2TL. Downward, what you're getting? mg. So if you want to remove that fellow, no, you'll get tangents like this. We need to apply some extra energy. It will rise to stick to liquid. The extra energy or work done required to remove the object from the surface is known as what we can tell. We can tell as surface energy, which we can tell that symbol is nothing but W. W equal to F into S, we can write it. This F is nothing but what means force due to surface tension here. Therefore, work done equal to TL into ds, we can write. Work done equals to T into dA. Therefore, work done equals to T into change in area, which we can write here. That is nothing but about the surface tension and surface energy, which we can tell here. Yes. Next topic, what we're going to discuss here means we're going to discuss excess pressure in a liquid drop or soap bubble. We're going to discuss here. So, what we're going to discuss? Excess pressure in a liquid drop or air bubble or soap bubble. We can discuss all the things can look similar. Let me discuss about one thing, then we'll conclude remaining one. So what we consider means, for example, we're having one bubble here, like this bubble we're having, whose radius is r, whose pressure is pi. We're having here. So what will happen means, if let me take outside pressure is P naught. If inside pressure is more than outside pressure, now what will happen? That bubble will get expands like this. Like this bubble expands. So what is the new bubble radius means? R plus dr. R plus dr means the dr value I'm considering is very small. This dr expansion is very small. Very small, which we are considering here. So inside pressure is more means outside pressure is less means what will happen means it will get expanded. So what we need to check? We need to check excess pressure, Pi minus P naught. We need to check. How to check Pi minus P naught? Pi minus P naught equal to what I can tell, inside minus outside can be written as excess pressure. Excess pressure, which we can tell. So you know that work done equal to T into delta A. We know delta A is nothing but what? Change in area. Just now we learned that. And here T is nothing but what we learned here? Surface tension we learned. So if I apply same formula here now, so F into delta x displacement is equal to T into delta A. Delta A is what? Change in area A2 minus A1, which you can write it here. So change in delta, change in area if you write here, no? So force due to surface tension is how much we can write it here. Force due to surface, force due to pressure if you write here, no? What we can write here? Pi minus P naught into area into dx at delta x equal to surface tension into area of 2 4 pi r square, but r value is how much? R plus dr, outer one, minus inside one 4 pi r square. Observe here na, r plus dr na, r plus dr whole square. This is r na, r whole square we writing. So this thing how you might be written, you might be having doubt. Force into area, so pressure into area nothing but force. Why? Because you know force is nothing but what we know here. Force is nothing but pressure. Sorry, 1 second. I'll teach you some basic. Pressure equal to what we're having? Force upon area. Force equal to pressure into area. From that we written pressure into area is nothing but what we can force. Fine. If we discuss here, no, how can you expand this value? Means you can expand like this. Pi minus P naught into area into dr equal to T into 4 pi into. So what we can write here? If you expand that, r square plus dr square plus 2r dr. 4 pi I took common here completely, means 4 pi I took here directly outside here, means what will get it here? Minus r square will get it here. See, if you observe here, no, this r square value going to be 0 and dr square value tending to how much? Means dr square value tending to 0. Why? Because if r value is small, let us consider like 0.2, r square value is how much? 0.04. That will become still more very value which can be negligible here. I told you expansion is small means dr will be small. So if dr will be 0.2, dr square value is how much? 0.04. That's why this dr square also can be negligible. Therefore, what we'll get it here means we'll get like this here. Pi minus P naught, Pi minus P naught into area. Area value is how much? 4 pi r square into dr equal to T into 4 pi into what remains here? 2r dr remains. 2r dr. So 1 dr will get cancelled here, and 4 pi will get cancelled here. 2t 1r will get cancelled. 2t divided by r will get, when r is remains here, na, r power 1. If it comes to LHS, r. Therefore, what will get it means Pi minus P naught equal to what will get it here? 2t divided by r will get it here. So this is nothing but excess pressure in a bubble. So only liquid bubble means what you get it here like this, and a complete liquid will be there. This is only liquid, no air inside that. For example, if you want to know about the air bubble, no, air bubble will get like this here. It's completely liquid. Like this. So here what you can observe here in this only air, in the inside that no liquid, only air, no liquid. So for liquid bubble is how much we got it means 2t by air r, na. So for air bubble also how much we get it here. So this is only we'll get for air bubble also. Air bubble also 2t by r. Next you have to tell for soap bubble how much we'll get, we have to tell here. For soap bubble, for soap bubble, So for soap bubble, if you want to discuss here, no, for example, if you take here, this is soap bubble you take. Inside one layer you can observe here, and outside also you can able to observe one layer here. Like this you can observe two layers. So inside what will be there here? Inside air will be there here. Outside what will be there here? Thick liquid will be there here. Thick liquid. So inside pressure how much you are considering? Pi. Outside pressure how much I am considering? P naught I am considering. Therefore Pi minus P naught equal to 2 into 2T by R we have to write. Why? Because two layers is there. One is inside air layer, outside is nothing but thick liquid layer, which we discussed. We are able to observe here. That's why 2 into 2T by R. That's why Pi minus P naught equal to what we can write here? 4T by R. So R is nothing but radius of curvature of the liquid bowl. And you have to observe here clearly, for liquid drop or for air bubble, you will get 2T by R. For soap bubble, what you got it? 4T by R, which will get it here. But generally, how can you conclude this thing means here? If you observe here, no, in general, case, what we can, how can we write this equation means we can write like Pi minus P naught equal to T into 1 by R1 plus 1 by R2 here. And one point should be clear right here. What is meant by R1 and R2 means R1 and R2 are radii in mutually perpendicular distances. Perpendicular directions. For example, if you take any sphere here like this, so if you consider one radii in this direction means another radii should be perpendicular to that nana, like this. In this direction, another radii you have to choose. So for your eye view, this is both should be perpendicular to each other. Means if you observe here, no, for this case especially, this direction also R, this direction also R. 1 by R plus 1 by R. 1 by R plus 1 by R is nothing but 2 by R. Therefore, if you observe here, no, Pi minus P naught equal to T into, for both 1 by R plus 1 by R, na, this case. So, Pi minus P naught equal to 1 plus 1 is how much? 2T by R. So, this is how we'll get by general formula for liquid drop. For example, if you're having two layers on here, 2T we have to write. If you're having like 3 layers, no, 3T we have to write it here. So that's what we need to do. For example, if they ask you for cylindrical surface. For cylindrical surface. Cylindrical surface. Cylindrical surface means they given one surface like this. They given one surface like this. Like this surface is given. For this surface, we need to write surface tension. How to write surface tension? If you observe here, no, this radius you can check clearly here. This radius is how much here from here to here. Horizontal radius R. But if you observe this vertical radius, will it closed up? No, it looks like open pipe. No, this radius is nothing but up to infinity. We can tell here. That's why I'm writing here. R1 equal to R. I'm writing R2 equal to how much I'm choosing infinity. So you're going to substitute in general formula. Pi minus P naught equal to T times the 1 by R1 nana. 1 by R plus 1 by R2 is nothing but infinity. Infinity value is how much? Anything about infinity is nothing but 0 nana. So 1 by R. Therefore, Pi minus P naught can be written as what we can write it? T by R. So for any cylindrical surface, Pi minus P naught value can be written as what here means T by R. T is nothing but surface tension. R is nothing but radius of curvature of the cylindrical pipe, which you can tell here. Yes. And next, what we are going to discuss means we are going to discuss applications of this topic, which we have learned here. So in this application, what we are going to learn first means we are going to learn combining of two soap bubbles. Soap bubbles. Very important topic. The same topic where you can see means you can able to see NCERT numericals. Same thing they will be repeatedly asking in NEET. Recently they asked in mains also. So everywhere these topics are important here. So let us consider two bubbles here. One bubble is there like this. Another bubble is there like this. Let us assume here. Smaller one radius is R1 I'm considering, pressure is P1. Bigger one radius I'm considering like R2 and pressure I'm considering like P2 here. So this pressure is how much outside pressure P0 I'm considering here. Generally just now we learned that for this thing delta P equal to what we got it for soap bubble 40 by R. Means delta P is inversely proportional to R. Means delta P is inversely proportional to R means wherever radius is less, no, their pressure will be more because inversely proportional. No? Therefore, here you can observe clearly R1 is greater than less than R2. Means what we can write here? P1 is greater than P2 which can tell. Therefore, P1 will be more now. So which type of shape you can observe means you can observe here like this. No? Like this it will become. So what will happen means P1 region will become concave. So here whose pressure is more means one pressure is more. No? So that's why you can conclude like this. No? Pressure from bubble 1 starts gushing into bubble 2, eventually bubble 1 becomes a small drop and bubble of new radius small r is formed. Means this bubble pressure we have to relate, this pressure bubble we have to relate. Now another new bubble is formed here due to these two. That one also we need to write here. So for this bubble P1 minus P2 divided by equal to 40 by R, we can write it here. So let me write equations for all the things here clearly. So first what we are writing here for bubble 1 Nana. For bubble 1. What we can write equation? P1 minus atmospheric pressure equal to 40 by R1 we can write it. That is you can make as equation 1 for bubble 2. P2 minus P0 equal to 40 by R2. This is equation 1. This is equation 2. Now what we are going to do, we are going to subtract here. This will become negative, this will become positive, this will become negative. These both will get cancelled. P1 minus P2 equal to what will get it here? 40 if we take common, no? 1 by R1 minus 1 by R2. Make this as equation number 3. We discussed here new bubble of radius R is formed. Now what is the new bubble equation we can write means here? P1 minus P2 equal to 40 upon new radius is R we can write here. So make this equation number as 4. Observe 3 and 4 here. If you observe 3 and 4, LHS are equal. LHS are equal means, so 40 by R equal to what we can write, Nana? 40 times 1 by R1 minus 1 by R2 which will get here. So if you observe carefully here, this 40 will get cancelled. 1 by R equal to what we got? 1 by R1 minus 1 by R2. So if you take LCM here, no, R2 minus R1 divided by R1 not we got it here. To reciprocate this equation, you'll get like R value, R equal to R will get it, R1 into R2 by R2 minus R1 will get it. This is nothing but new radius, we got it here. No new bubble radius if we got it here. So nothing is here. For 1, we need to write one equation. For 2, we need to write equation. For new bubble, we need to write one equation. You just compare all three equations. You'll get like 40 will get cancelled. R equal to R1 R2 by R1 minus R2 minus R1 we can write here. This is nothing but R2 is nothing but bigger radius, R minus R1 is nothing but smaller radius. Okay. So if you observe here, this is for two bubble. These two bubbles are we combining. Next in JEE main 18 they asked one application here. What they asked in that application means when they asked JEE means 18 they asked here. So what they ask means here a bubble inside in another bubble. So what they're asking is, for example, if this is the case, outside bubble, this is inside bubble. Inside one radius is R1, outside one radius is R2. Inside pressure is how much means P1, outside one pressure is how much P2. Atmospheric pressure is how much P0. And this bubble is going to expand inside one. As a result, one new bubble is forming whose radius is R, whose pressure is P0, which is there here. They're asking here. Inside pressure will be P1. Now, if you observe here now, what we have to do, these two we have to replace by a new bubble, where inner sphere pressure is how much P1, outer sphere pressure is how much P0. We have to mention that point here. Replace the system by a single bubble whose inner pressure is P1 and outside pressure is P0. Why? Because radius is small, no? For inner one, radius is small means pressure will be more. That's why inside pressure only considering almost outside pressure. This bigger one also. So, for example, if you write equations, no, for bubble one, if you observe here, what we can write now? P1 minus P2 equal to 4T by R1. Why? Because observe, this is P1, this is P2. For second bubble, if you write now, P2 minus outside one, P0. So for bubble 2, what you can write here? P2 minus P0 equal to what we are having now? 4T by R2. Just have to do what means, you just have to add these two. Minus P2 plus P2 will get cancelled. P1 minus P2 will get P1 minus P0. P1 minus P0 equal to what will get here? 4T times the 1 by R1 plus 1 by R2, which will get here. Now you write equation for new bubble. If you write equation for new bubble, observe P1 outside what will be there? P0. So what I can write for new bubble? For new bubble, P1 minus P0 equal to 4T by R. Let me make this equation number 1, equation number 2. Compare 1 and 2. If you compare 1 and 2, P1 minus P0, P1 minus P0. If LHS equal, RHS should be equal. So 4T by R equal to what we can write? 4T times the 1 by R1 plus 1 by R2. This fellow will get cancelled. 1 by R equal to 1 by R1 plus 1 by R2. You can got it here. So if you take R equivalent, what will get? R equivalent is nothing but R1 into R2 divided by R2 plus R1. So if two bubbles you are combining, what will happen means R1 R2 divided by R1 minus R2, you got it here. If bubble inside the bubble, R1 into R2 divided by R2 plus R1, just formula changes there, just have to remember that. And I told you one question they asked in JEE 18, let me give you that question what they given means. So this question they given here like this, inner radius how much they given, outer radius they given like 6 centimeters, okay, inner radius how much they given 4 centimeters, then calculate R equivalent. So if they ask us to calculate R equivalent, it's easy to find. So R equivalent can be written as what here? R1 into R2, 6 into 4 divided by 6 plus 4, 6 plus 4, that equal to 6 into 4 divided by 6 plus 4 is how much? 6 plus 4 is nothing but 10. So 10. So 6 4 is 24. 24 by 10 is nothing but 2.4 centimeters, which we can tell here. This is the answer for which they given in that JEE question. You have to remember these formulas finally at the end of the day. R equivalent equals to R1 R2 divided by R2 minus R1. R equal to R1 R2 divided by R1 plus R2 which you have to remember. Fine, dear students. Now, in this slide, what we're going to discuss means two soap bubbles combines isothermally. Then find new radius they're asking here. Two soap bubbles combines isothermally. Then radius they're asking us here. For example, we're having two soap bubbles. Let me take whose radius is R1, whose radius is R2. These both are combined and it's forming like one new bubble here, whose radius is R. We need to calculate R. So isothermal case or vacuum case also will get both same. Combined in vacuum, if they told also, you have to consider same solution which we are doing here. So for soap bubble case, what we can consider means for soap bubble. So basically what is conserved means mass is conserved here. So mass is directly proportional to what we can tell here means here. Mass is directly proportional to surface area we have to write now. Surface area. Therefore, m equal to what we can write? m1 plus m2. From where I can conclude this? From here. m1 plus m2 you can write here. So surface area of new one is nothing but 4 pi r square. 4 pi r square equal to 4 pi r1 square plus 4 pi r2 square we are having here. This fellow will get cancelled. R square equal to r1 square plus r2 square will get. This is the answer for this question here. They'll give values you can substitute here. For example, in the place of soap bubbles, they mix here liquid bubbles they're doing now. Liquid drops otherwise. Liquid drops they given. They given two liquid drops like this. Whose radius is R1, whose radius is R2. They combine and it's going to form a new drop of radius R. Liquid drop means usually what will be there inside liquid will be present na? Like this. Like this. So here mass is conserved still. So what we can write? Mass is directly proportional to m1 plus m2. What we can write means here since everywhere mass is there inside also. So mass is directly proportional to what I can tell means here volume nana. So mass is directly proportional to volume means m1 plus m1 equal to that is this. 1 second here. Okay. So this mass let be considered as m. This mass let be considered as m1. This mass let be considered as m2. So m1 plus m2 should be equal to what? M. Therefore m equal to m1 plus m2. Since it is directly proportional to volume, now 4 by 3 pi r cube is equal to 4 by 3 pi r1 cube plus 4 by 3 pi r2 cube, which we given here, which we got it. 4 by 3 pi, 4 by 3 pi, we can take common, we can cancel with this fellow. Therefore, r cube equal to r1 cube plus r2 cube, which will get it here. This is the relation between r1 and r2 new radius when they combine liquid drops. When they combine soap bubbles, we'll get answer like this. Fine, dear students, our next topic is nothing but what we are going to rise means we are going to discuss about the capillarity rise or capillarity we are going to discuss here. What is meant by capillarity rise? Capillarity. So for example, let me take one example here. We are having one container Nana here. In this container, what we are having means we are having some liquid. Some liquid we are having. So you might be familiarly experienced in chemistry laboratories. So what we are going to do means here we are going to take one test tube and we are going to dip in this. So what will happen means that liquid will rise in this like this. In some cases it falls also. It depends which type of liquid here. For example, let me take this is water. So will rise like this. This phenomena is nothing but what we can tell here capillary rise. So the phenomena of the rise or fall fall of liquid in a capillary tube with respect to the surroundings is known as capillary rise we can call. So for example, we need to discuss many tasks here. What we need to discuss means first we need to discuss angle of contact. We need to discuss what do you mean by angle of contact. Let me choose here angle of contact. So what is meant by angle of contact means here. So let me explain you. It is defined as the angle between the liquid surface drawn at a point contact inside the liquid surface is called what? Angle of contact. So let me write here. It is defined as the angle between the liquid surface drawn at the point of contact and the solid surface inside the liquid. For example, which a given example here, no? In this case, let me observe means, let me choose other color here. So this is liquid drop here now, liquid shape. Here you have to take one tangent here, and this is a solid surface here, like this you're having now. 1 second. Here you're able to see this liquid. This is solid surface. Here liquid shape is there now, like this. Here you have to draw one tangent here, and this angle is nothing but what we can tell angle of contact. For example, if I'm taking water here and I'm putting on one surface now. This is one surface. We're keeping one drop here, like this. It is from drop here. So you have to choose one tangent here. Oh, it's going away. You have to choose a tangent here, and this is a surface now here, and this angle is nothing but what we can tell here angle of contact. Tangent we are having here. This is the tangent, and this is nothing but point of contact, and this is the surface. This angle is nothing but angle of contact. And which type of angle we got it here? This case acute angle we got it. Acute angle theta value is less than 90, will get it. So solid line where will get it means inside the surface, which we got it here. So next what we need to, what we can discuss here means we can discuss. Let me take case system clearly. Case 1, we're having surface here. We're keeping liquid on this like this. If you draw tangent, how does you get tangent? We get a tangent like this, and inside the solid surface is this angle is nothing but which angle? This is nothing but angle theta. We got it here. So just now we learned that theta value is how much? Theta is less than 90. Which angle it is? Acute angle. So for acute angle, what will happen means liquid wets the surface glass. Liquid wets the surface of glass. Surface of glass. What we can tell? Example. You can tell like pure glass plus just glass plus water. Glass plus water combination. If you take and if you pour water in the glass, what will happen? Glass will wet. No, that is the case which we can tell here. Case 2, what we can discuss here means case 2. For example, you're taking here, and that if you pour some liquid, that's getting shaped like this, like this. So if you want to draw the tangent here, this is the tangent we are having here. This is a solid line inside the surface, and this is the angle here. We got it here. Theta acute or obtuse means obtuse angle, will get it here because theta is greater than 90 degrees. So which angle will get it means obtuse angle. Obtuse angle, which we got it here. So what will happen means whenever we get obtuse angle, no, liquid will not wet the surface. Liquid doesn't wet the solid surface. Example, it might be again experienced in chemistry laboratory. Mercury and glass. So mercury will not wet the glass surface. Next, another case is there here, case 3. In that case 3, what we are going to observe is for pure water, theta value is going to be 90. For example, we're having here water. We're having this capillary tube. In that water, how does it will go pure water on the glass tube means like this. So if you check here angle, no, angle between these two is how much, 90 degrees, right? So which case we can take here means for pure water, and clean glass. Yes, and what will happen means doesn't wet the surface. Wet the surface, which we can tell here. And capillary rise, nothing but rise or fall is there. No? In this case, what are the things we can take means we can take concave meniscus, convex meniscus we can take here. In this case, we can discuss about the meniscus, concave, convex. For example, we are having one capillary tube like this. Let it take here. Capillary tube of fine bore. Fine bore means this hole is nothing but nice one. We are having one capillary tube like this. For example, in that you got meniscus like this. Let us consider. So that meniscus is what we can call it as means that shape of meniscus is nothing but concave meniscus, which you can call. For example, you got like this meniscus. So that meniscus is called what generally means plain meniscus, which you can call it as plain meniscus. For example, you got like this meniscus. Like this meniscus, we got it means. So we can consider that is nothing but which meniscus, convex, convex meniscus, which we can consider. So where we get convex meniscus, concave meniscus, this all things means you can observe here. This theta capillary less theta value, Here what will get it means here concave will get it, here convex will get it, here plane meniscus, which you can observe here. If you take examples, again, we need not to discuss these examples here. Dear students, now we are going to study the rise of liquid Maximum rise of liquid in capillary tube. Important derivation for 5 marks for PU boards as well as CBSE boards. Maximum rise of liquid in capillary tube. See, first let me take here, you have to understand the diagram well here. We are taking one container here. This container, what we are placing means we are placing one capillary tube and we are filling with some liquid nana here. So eventually what will happen, that liquid will rise here, I'm assuming here up to this point. So liquid is rising up to this point. What will happen if I enclose this shape now, you're able to get like this bubble, you're able to observe here. And this pressure, outside pressure, how much I'm considering? P naught. And this radius, how much you're considering? Capital R I'm taking here. How can you draw the tangent here? Means we can draw the tangent here like this to the surface. This is a tangent and this is a solid surface. This angle is called, what we can call it as angle of contact theta, we can write it here. Let us take at this point pressure B, at this point pressure C, at this point pressure A. So basically this pressure B should be equal to pressure C. We studied in last lecture, pressure on a horizontal line should be equal, we can study it here. And if you observe here, this fellow, this capillary tube which you observe, no, let me draw that capillary tube diagram outside. You can able to see that capillary tube like this now. This is a capillary tube. And what is capillary tube radius you can take means this is the radius of the capillary tube, you see. On this capillary tube, you are able to observe one liquid drop like this. One shape like this, that's whose radius is capillary, which you can able to observe. Should not get confused that. That's why I drew diagram outside. Okay, let me take this diagram outside now. You're having this type of shape, which you'll get it. Let me assume here. And here, this is nothing but what we can call it as capital R here. And this is nothing but what we can tell here, small r. And this is nothing but tangent, which you're having here, like this. And this is nothing but solid surface. This angle is how much we are having here. This angle is theta. This angle is theta means what we can write, this angle 90 minus theta. This angle 90 minus theta we can write means this angle can be written as theta. So from here what we can write means cos theta. How can you write? Cos theta can be written as small r divided by capital R. Sir. Small r can be written as what we can write it? R cos theta. You can write it here. Small r equal to what we can write it? R cos theta, which you can write it here. So if you observe here now, here if you observe, outside pressure is P naught. P naught minus PA equal to what we can write it, Nana? 2T by R. For liquid bubble, we are right, that formula I'm going to apply here. For this fellow, this is what? PI. Outside is P naught we are taking. So PA, P naught. P naught minus PA is nothing but what we can write it? 2T by R. Therefore, P naught minus PA equal to what we can write? 2T by R. And if you observe here now, so PC equal to what we can write? PA plus rho GH we can write it. Variation of G with depth we written, that thing. PC equal to pressure at this point equal to, this is the height, Nana. Height up to where it is raised. Up to here only height it is raised. This is the height I'm considering. So about this point pressure equal to this pressure plus this pressure into height, Nana. PC equal to PA plus rho GH. If you observe here, no, this is open to the atmosphere and this is an horizontal line. PB equal to PC, that should be equal to what here? This is open with atmosphere, no, that pressure is how much? P naught. That's why I can mention that PB equal to PC equal to P naught we can write. If as a result equation, how can I write it here? P naught equal to, if it goes this side, no, plus, no, PA plus 2T by R, and another one P naught equal to, I can write PA plus rho GH, I can write here. So if you observe here, now what we are having here? Take minus sign, take minus sign, take minus sign, cancel. 2T minus rho GH equals to 0. 2T equal to what we can write here? Rho GH. Rho GH equal to 2T by capital R, which will get Nana here. So rho g h equal to 2t by capital R we got it now here. So now what we are going to substitute means we are going to substitute h equal to 2t by rho r g, you can write from here. So write first answer h equal to 2t by rho g r, rho g r we having here. So here small r equal to capital R cos theta, we can write it here. Capital R equal to what we can write now? R by cos theta we can write now. I'm just going to substitute that value. H equals to 2t divided by rho g r divided by cos theta. Therefore 2t cos theta by rho r g or rho g r, height of the liquid which is raised here. So you have to analyze some points here. First point what we need to analyze means here, for example, first point, height to which liquid raised is called h equal to what we can tell means 2t cos theta divided by rho rg. Second point what we can tell, for given liquid if tangent, theta and density are constant, then what will happen means these all things will remain constant except what here, radius. G value already constant, we know that here. So what will happen means, so h is inversely proportional to what we can tell, r. Therefore h2 by h1 can be written as what means r1 by r2. These all the concepts will be useful in numericals while solving in numericals. For example, density equal to what we know, mass by volume, we know, right? So that can be written as what, mass by area into height we can write now. So that can be written as from here. So h can be written as what from here, h equal to m by rho a we can write now. So h equal to m by rho a means m into rho by pi r square we can write it. So h equal to m by rho pi r square we're having, h equal to another formula we're having here. We're just going to equate this both here. So h equal to 2t cos theta by rho rg na. So h equal to another formula what we're having, m by rho pi r square equal to 2t cos theta divided by rho rg which we are having here. If you observe, density will get cancelled, 1r will get cancelled. Therefore if you observe here now what will happen, m by r will become like constant. M by r equal to this pi if I send also this theta, these all things you can say as constant means m by r equal to what I can tell here, m by r equal to constant which you can write here. M by r equal to constant means what we can tell now, you can compare m2 by m1 equal to r2 by r1 which you can write here when we need to compare with the mass of the liquids in the tubes. This is nothing but capitalize. So up to you have to write for the derivation. They'll give 5 marks. You have to give this theory also. Finally, we discuss some applications of capillarity. So what they're asking means, if two capillary tubes of, they're telling one task, they given one task here. In the task, what they're telling here means, if two capillary tubes of radius r1 and r2 greater than r1 means unequal lengths are dipped in a liquid, then difference in the level of liquids, difference in the height level of the liquids. For example, let me consider what they're telling the case is this case. We having container, up here we have filled with some liquid. Now what we are going to dip here, we are going to dip the two capillary tubes like this. This is one capillary tube. This is another capillary tube whose bore is little larger one. This is R1, this is R2, you assume. So for example, in first one, liquid is rising up to this level. Let me take this nothing but H1. And second one, liquid is rising up to this level, H2. Difference between these two heights we need to get to know here. This is very simple here. So since H is inversely proportional to R, what we can tell here, where R1 is less than R2, no? What will happen? H2 will be greater than H1, will get it here. So delta H, if you want to calculate, no? Delta H equals to H2 minus H1. So what is we just written here? 2t cos theta upon rho g r rho g, no? 2t cos theta upon same liquid rho r2g minus 2t cos theta upon rho r1g. So if you take common here, delta H equals to what we can write it? 2t cos theta over rho g we can take common 1 by r2 minus 1 by r1 we can write it here. So delta H equals to what we can write here? 2t cos theta upon rho g into, we take LCM, r1 minus r2 divided by r1 into r2, which will get it here. This is exactly NCERT concept which is here, the same thing which we have learned here. Application of capillarity. The similar application is there, another application. In that application, what they're asking means they're asking like this. This is also NCERT concept only. What they're asking means this is actually NCERT concept. In this, two capillary tubes radius R1 and R2, R1 greater than R2 are joined to form narrow U-tube. The difference in the level of the liquids in both the tubes is see what the concept they're asking here means. Basically they given two tubes and like this, two capillary tubes they took like this. This is one tube and they want to choose another tube here whose radiuses are not equal. One should be larger, one should be smaller one, like this. What they did means they joined these both here together like this. And if you fill the liquid here, no, that fill is unequal heights. So in this up to here, its K means in this tube, capillary tube, in this up to here it is formed. Up to here. If you observe, this is the reference level. If you take here, no, this height is how much you can take here, H1. This height is how much you can take here, H2. Difference means what we can do here. Again, same thing, delta H equal to what we can write here, H2 minus H1. Therefore, delta H equal to H2 value, what we can write it here, 2t cos theta upon rho Rg, rho into R2 G. R2 you take, R1 you take, minus 2t cos theta upon rho R1G. So take 2t cos theta by rho G common. 2t cos theta upon rho G if you take common, now what we can take here, 1 by R2 minus 1 by R1. So you take LCM, again you will get around same answer, you will get it. And for solving numericals, this type of applications are very important, which is there from NCERT. They can ask you for JEE, NEET and all. So let me discuss some important points of these fluids here. Today what we have learned here means what we skipped there. So what we require means work done to forming a liquid drop bubble. How much will get means basically work done equal to what we're having, tension into delta A, right? So work done can be written as tension into 4 pi r square, we can write it here. So therefore work done equal to 4 pi r square T, where T is nothing but surface tension, we can write it. That stands for F by L, we learned now that one. Second one, what I want to know, it means work done in increasing size of the bubble. So work done equal to what we can write means T into delta A, 4 pi r square. Now that r square we have to write initial minus final, 4 pi r1 square minus r2 square. For example, next one I want to comment on work done in forming a soap bubble. A soap bubble of radius r. How much is required means work done equal to 2t into what will get 4 pi r square. That's why, no? Why? Because soap bubble having two layers, I told you. One is inner layer, one is another layer, outer layer. That is air layer is one layer, soap layer is one layer we have. Next point, what we need to discuss here means we need to discuss work done in increasing the size of soap bubble from R1 to R2. So work done equal to what will get means work done equal to 2t into 4 pi R2 square minus R1 square, you can write it. Therefore work done equal to 8 pi t into R2 square minus R1 square. These are the small applications where we need to remember, and where we'll get sometimes direct numericals for this NEET, JEE, CET and all. Thank you, dears. This is for today's class, and we are done with this chapter. Thanks for watching.